So hello everyone, this is lecture 34 for the mathematical physics. In the last lecture we discussed about the continuity and limits of a complex function, and we defined that how we can check that if function is continuous or not. And we have seen this example, we have find it means we considered actually the three directions on which we will check that if function is continuous, then we will say that function is continuous if it is continuous in these three directions. Those will be, first we will take x is constant and we will approach means x is constant, then we approach y to 0 means y to z naught. Okay, and then we will take y as constant and we will approach x as tending to z naught. Okay, so these are the two directions. Then third will be y equal to x, we will take this direction, and taking both equal to 0, then that x or y either can be tending to z naught. So those were the three directions. You can check the last lecture, it will be more clear to you. Now we have taken this example already. Now let's see one more example. If fz equal to this real z over 1 plus mod z, so we need to check at z equal to 0 the continuity of this function, and the value of function at z equal to 0 is given, f0 equal to 0. So fz is, real z will be x, if we consider z as x plus iota y, then real z will be x, 1 plus mod z will be under root x square plus y square. Now let's consider these three directions. For x-axis, y should be constant, means y equal to 0, and we have considered x-axis, so x will be tending to 0, but y will be 0 and x is tending to 0. So we will put y equal to 0 in this, so we'll get x over 1 plus mod x. Now x is tending to 0, so first you can write this mod x as plus x for x greater than 0 and minus x for less than 0. Now for either value, means x is tending to 0 here, so you will get 0 in both the conditions. Putting x equal to 0 here, 0 here, you will get 0. So for this direction you are getting the value same as f0 equal to 0. Now let's consider the second case, means we put x equal to 0 and y will be tending to 0. So in that case, x equal to 0 you will put here, then you will get again fz equal to 0. So this both directions giving us the same value, that is f0 equal to 0, and this condition is also giving us 0, this is also giving us 0. Now let's check the third direction, that is y equal to x. So we'll put y equal to x here, so you will get under root 2x from here and x here. Now x is tending to 0 because both can be 0, y tending to 0, x tending to 0, but here y equal to x, so we can substitute anything here. So for x it will be x tending to 0, so this x will be 0, then this whole term will came out to be 0. So then we will call this function as continuous at z equal to 0, because we are getting the same limits in all the cases. So that's how you check if function is continuous or not. Now let's see the derivative. So how we can say that if function is derivative, means is derivative defined or not. Okay, so the derivative of a complex function fz at z naught is defined as, first let's see the definition, that how we define the derivative of a complex function. That is f dash z naught at z naught, the derivative of f will be denoted by this sign, means dash. Then limit delta z tends to 0, f z naught plus delta z minus f z naught divided by delta z, and delta z is tending to 0. So that's how you define the derivative. It's just like the same as you find in the real functions when it was dx over something, means df over dx, dy by dx. So there you find out that it was x plus delta x minus fx divided by x, means delta x. So you consider their h value, so it was x plus h x divided by h, and h was tending to 0. It's just same in the complex plane also, we are having the same definition for the derivative, but now this z is nothing but complex number. Okay, so provided the limit exists, so if the limit exists, where means if this is defined, this limit is defined, so we already know that how we check if a limit is defined or not. We have to check from the three directions. If it is defined, then we will say that this limit is defined. So if the limit exists, then delta z, then we call that as, means it is derivative is defined. Okay, so delta z is z minus z naught, f dash, means this also can be written as fz minus fz naught divided by z minus z naught. Okay, because delta z is nothing but z minus z naught. When you substitute it here, you will get this fz, where z is tending to z naught from any direction in complex plane. So that's how you check. Means z naught can be any point, and then you will check at that point the continuity or the limit. Then if you are getting the same value, then this derivative will be defined. So let's see one example. So fz equal to z square. Now f dash z will be limit f z plus z naught minus fz divided by delta z. This is our derivative. So let's check. So what is z plus z naught? It will be square of z plus z naught minus fz will be z square divided by delta z, and delta z is tending to 0. Now let's open the square. You will get z square plus delta z square plus 2z delta z minus z square. This will cancel out. You can take delta z common. You will get delta z plus 2z, and this will cancel out. So now putting delta z equal to 0, you will get 2z as your answer. Okay, so now this is a defined function. Okay, so we will say that function is differentiable, and here this formula is also applicable. Means you can directly find the derivative, that is z square, like x square you get 2x from here also, z square will give you 2z. Okay, so it's just like the same in here also. So let's see some rules of the differentiation. So it's just like in the real functions, here also we have some rules to find the differentiation fast. So rules are, if there is two functions fz and gz, and c is some constant and f is our function of z, then derivative will give us c f dash. Okay, c is constant. F plus g derivative will give us f derivative plus g derivative. When there is product of functions, then first take first one as it is, then derivative of second plus f dash plus g. When it is in divide, then square of the denominator function, put it as it is, and f dash minus g dash f. So these rules are just the same as in the real functions, so it will be easy to remember. Okay, so remember all these formulas. Now let's check some functions if they are differentiable or not. First let's check about this is conjugate z, and we get this information from here, that all kind of polynomial functions, means z square, z cube, or 1 or anything, these all will be differentiable. Okay, because you know this limit will exist everywhere in all kind of polynomial functions. So remember, this kind of functions are differentiable in all entire complex plane. Okay, so let's see this one. fz is z bar, means fz is z conjugate. So let's check if it is differentiable or not in the complex plane. So z naught can be any point in the complex plane, and we are tending to that z naught from any direction. So delta z will be tending to 0. So differentiation is this: fz plus delta z minus fz divided by delta z. Fz plus delta z will be conjugate of this minus z conjugate divided by delta z. Now this will open to this z conjugate plus delta z conjugate minus z conjugate divided by delta z. This will cancel out. Now we'll get limit delta z tending to 0, delta z conjugate divided by delta z. Now z is nothing but x plus iota y, and delta z will be delta x plus iota del y. Just substitute the values. So delta z will be, and conjugate will be delta x minus iota delta y. So we substitute it here and here. Now we will check in all the directions. First let's check along the x-axis. Okay, put delta, means y is constant, then y is constant, then delta y will be 0, and delta x will be tending to 0. Means like this, we having this point somewhere, and this y is constant, so delta y will give us 0, and at the x-axis we are tending to this point, so this difference will be tending to 0, so delta x will be tending to 0. Now put delta y equal to 0 here and this, so we will get 1 as your answer. Now for y-axis, now we will put this x as constant, and on the y-axis we will tending to that point, so delta y will be tending to 0, and delta x will be 0, so this will be 0, and we will get this will cancel out, we'll get -1 here. So these two are different, so limit does not exist, so that's why we'll say that this function is not differentiable. So we'll call that this conjugate of z is not differentiable at any point in the complex plane. Okay, because we find it this case for a general solution, any z naught point, so it is not differentiable. Remember this is very important result. Now what are analytic functions? So it's just a simple thing that a function which is differentiable, then we call that function as analytic also. A function fz is said to be analytic in some domain, in a particular domain which contains some points in complex plane if it is defined and differentiable in that domain. So if there is this region and the function is differentiable at all points in that region, then we will say that the function is analytic in that domain. Okay, so if it is defined and differentiable in that domain, then we call it as analytic. A function fz is said to be analytic at point z naught. A particular point, if we are talking about a particular point, then we will call it analytic at point z naught if it is analytic in a neighborhood of z naught. So it will be analytic at that point when it is in analytic at nearby points. Okay, so it's like the same, means it should be differentiable at the z naught, only we will call that analytic there. Okay, so the same condition as we talked earlier about the differentiation is same as for the analytic. So let's see some conclusions. The non-negative integer powers power should be 1 2 3 4 and means they should be integer and should be non-negative. Then they are all analytic in entire complex plane. I already told you this thing. And we call these functions like z square entire function because they are differentiable at or analytic at all points in the complex plane. So this function is also analytic because it is sum of these polynomials, and here it can be c2 can be 0, c3 can be 0, then you will get this function or this function, means these all are differentiable and analytic in whole complex plane. So analytic in an entire complex plane. Remember this, when you get this you don't need to find anything, you will just say that the function is analytic. Now if this kind of function is given, fz is gz over hz, and gz and hz are this kind of functions, means polynomial type. So we will say that this function is also analytic at all points except only those points where hz is tending to 0, means hz equal to 0. So only at these points, means where only at those z where this hz becomes 0, at all those points the function will be non-analytic and it will diverge. Other than that all points are in the analytic function. Okay, so this was the case. Now let's see CR equations. We call them the Cauchy-Riemann equations. So this is a necessary condition, means it's not need to be true that if this satisfied then the function will be analytic, but if this does not satisfy the function will not be analytic. This is a necessary condition, this should be satisfied. Okay, so let's see. Derivative of z is defined by, we know how derivative defined, fz plus delta z minus fz divided by delta z, and when delta z tending to 0, we will get as this is nothing but delta f divided by delta z. So and this is known as differentiation, so we'll call this df by dz. Remember this is our differentiation, df by dz, when this delta z is tending to 0. So f dash z, we denote it like this. So remember these expressions. Now we will consider two cases for any point z naught. It can be any point in the complex plane. So we'll consider these two statements. I will come here later. So first, this is our differentiation, and if fz is some complex function, it can be defined in terms of u plus iota v. So I already told you how kind of function is this, where z is x plus iota y, then delta f over delta z will nothing but delta u plus iota delta v divided by delta x plus iota delta y. So remember this condition. Now we will consider these two cases, means these are the two directions we will consider to find the differentiability. So first we will consider this x as constant, so delta x will be 0 at this point, and delta y delta y will be tending to 0, means we will consider all the nearby points on this line. So delta y will be tending to 0 and delta x will be 0. So substitute here delta x as 0 and delta y is tending to 0, so we will get this equation, means this will be 0, so it will be delta u by delta y and delta v by delta y. So this is the second case. Let's consider first case first, then second. We'll come to this later. So first case is delta x is tending to 0 and delta y is 0. So we are considering this line. So at this line y is constant, so delta y will be 0 and delta x is these nearby points. So after substituting delta y equal to 0, we will get delta u by delta x and delta v by delta x. And we already defined this condition, limit delta x tends to 0 and delta u by delta x is nothing but this df by dz, or in the partial differentiation you will write as delta u by delta x here, because u is a function of x and y and you are having only the differentiation with respect to s, so you will write its partial derivative. Okay, and this will give you iota delta v by delta x. So I hope it is clear to you how we get this expression. Now same we will use the second expression. We will put delta x equal to 0 and delta y tending to 0, so we'll get delta u by delta y plus iota delta v by delta y. Means here we will get let me tell you, delta u divided by iota delta y, so it will give you iota multiply, so we'll get minus delta u by delta y. So let's see the second case. So we'll get this condition. So delta u plus iota delta v divided by iota delta y, because delta x is 0 here. Now this, take this denominator into denominator of both of these, so you will get minus delta u by delta y plus del v by del y, because iota will cancel out, so you will get this condition. Now you can compare these two cases, because this limit should be equal, only then this derivative exists. So this part should be equal to the real part of this, delta u by delta x should be equal to delta v by delta y, and imaginary part should be equal to imaginary part. So delta v by delta x should be equal to minus delta u by delta y, so it will be like this. So these two conditions are called the Cauchy-Riemann conditions. So these are the basic conditions which should be satisfied. Only after that we can say that it can be differentiable or not. But if this is not satisfied, then we will call that it is not differentiable at all. Okay, so in order to df by dz exist, CR equation must be satisfied, so these conditions should be satisfied. Now what are the necessary and sufficient conditions to say that the function is differentiable? If CR equations are satisfied and the partial derivative, now these equations are satisfied. Okay, now we have to check one more condition. The partial derivative of uxy and vxy, means these u del u by del y del vy, all four terms, these should be continuous. If they are continuous, then we will say that derivative of df by dz exists. Now finally we can say that. So let's take one example. Fz equal to z square. So z is nothing but x plus iota y. So if we square that, then we will get this real form and the imaginary term will be this. Now we have to check the CR conditions. So it will be delta u by delta x. So compare this equation first. This will be our u, this will be our v. So delta u by delta x will be 2x and delta v by delta y will be 2x. Delta u by delta y will be minus 2y, and here also delta v by delta x will be 2y, but if you put minus here you will get this. Now see, these two are equal, these two are equal, so we will say that the CR conditions are satisfied. Now you can see these all four are equal to this 2x and minus 2y, and these are continuous, means 2x is continuous definitely and minus 2y is continuous. You can check this. So if they are continuous also, then we will say that fz equal to z square is differentiable at all points. Okay, and we already know this, that this is a differentiable function in the entire complex plane. So okay, that's it for today. Thank you everyone.